currently an assistant professor at the University of British Columbia in Canada. And my research focuses on developing new organic reactions and catalysts with machine learning and computations. As you can tell, I'm not from here. I'm originally from Northern Ireland, and I got my master's from Queen's University Belfast. I then moved to the University of Cambridge to undertake PhD studies with Professor Jonathan Goodman, and in that role, I did both experiments and calculations to try and understand the reasons for stereoselectivity in catalytic asymmetric reactions. Not liking to stay in one country for too long, I then jumped across the pond to the US to work with Matt Sigman at the University of Utah as a Marie Curie postdoctoral research fellow. In this role, and with the help of a bunch of experimental collaborators, I was able to build statistical models to predict organic reaction outcomes for many important catalytic systems. Jun Shan, the first author of the paper that we're discussing today, he grew up in China and got his PhD from ICIQ in Spain. He really focused on immobilizing important chiral catalysts and applying them to create more efficient reaction systems. He joined my group in May in 2021. So he's been here slightly over a year and has been instrumental in developing organic reactions and catalysts and getting the lab up and running, which is really important as a young assistant professor. So he's been a real great help. So I've always been interested by asymmetric catalysis ever since I was introduced to the topic in my undergraduate studies. But I didn't get a chance to work on this until Jonathan Goodman introduced me to chirophosphoric acids. And these have been my favorite catalysts ever since. I've been so intrigued by how well they work, and for so many reactions, I just needed to find out why they work so good. My first studies focused on Bronsted acid reactions with pyrophosphoric acid catalysts. In these systems, the catalyst will donate a proton to a basic electrophile, priming it for nucleophile attack. The large groups on either side of the catalyst will impart an anti-selectivity by determining how the reactants fit inside the chiral pocket. But how chiral phosphates impart an anti-selectivity in the reactions is more mysterious. And so we've been trying to understand this for the last few years. So prior to the ChemSci paper, we actually studied reactions involving iminiums with chiral phosphates. And we found that iminiums bind to chiral phosphates through unusual hydrogen bonding interactions. And these contacts are really important for an anti-selectivity. The obvious question is, do other intermediates also interact with chiral phosphates in a similar way? And so that led us to study thionium reactions. Of course, there isn't many in anti-selective versions. So that led us to theoretically investigate the additions of amines to thioniums to produce NS-acetals. We performed computations to get a better picture of the transition state structures involved in the key bond formation steps. That allowed us to investigate or visualize that thioniums do interact with pyrophosphates in the same way as iminiums through these unusual type of hydrogen bonding contacts. But what the computations predicted and what we got, or what had been observed by experiment, did not agree. In other words, our computations predicted the other enantiomer to be favored than what was found by experiment. So of course, we went to our calculations, checked for errors, couldn't find any. To explain the differences between experiment and computation, we also tried a few more computations. It's really important to test a variety of different basis sets and functionals, which is just different flavors of how to produce accurate molecule geometries and energies. And these led to the same conclusions. Of course, now we caved in and performed the experiment in our own wet lab, which was just getting set up at the time. So this was probably the first reaction we actually formed, the first reaction that we actually ran in our wet lab. And we got the product. The EE was the same as what had been found by the previous group. We grew the crystal, took it to Brian, our resident crystallographer, and he was able to solve the absolute stereochemistry of that structure. And I guess it was lucky, but it confirmed your calculations were indeed correct. But we weren't necessarily convinced by this, or at least it wasn't enough to convince us. So we had to check that we were working with the correct enantiomer of catalyst. And so we confirmed the absolute configuration of vinyl. And indeed, we were using what we thought we were using. So we believe that these types of unusual hydrogen bonds also exist between cationic intermediates and other catalysts that are anionic. And so we are actively exploring this. Perhaps more importantly is that chiral phosphates do not catalyze as many reactions as chiral phosphoric acids. We hope that our mechanistic studies will inspire people or other investigators to come up with bolder reaction designs that rely on unusual hydrogen bonding contacts rather than the conventional acid-base interactions. We want the chemical community to trust our work, believe that it's important and impactful. We also want to make our work accessible to a broad audience. Chemical science allows all of this through their rigorous peer review, the excellent work that it publishes, and their open access platform. And these are the three key reasons that we chose chemical science.